Welcome back. This is the second episode and the third chapter of the Crystal Clear Electronics videos. Dear Danyi Béla, please summarize what we will talk about in this chapter.
In this video, we mainly update our knowledge of DC currents, including resistors, different sources, and the concept of power. We will also briefly discuss AC voltage. Let's start right away with the concept of electric current. If we connect two different charged bodies with a metal wire, we can notice that electrons move from the more negative body towards the more positive body.
Azt vehetjük észre, hogy elektronok vándorolnak át a negatívabb test felől a pozitívabb test felé. A töltések tartós egyirányú.
The flow of charges is called electric current with capital I. The electric current shows how much charge flows through the conductor in a given time. Its unit of measurement is ampere with capital A. Mathematically, I equals delta Q over delta T, where Q is the amount of charge. If electric charge moves from one place to another, may it be any charged particle, then we're talking about electrical current. In liquids, for example, not only electrons can move, but also atoms that have electron deficiency or excess. They are the so-called ions. In any technical drawings, the direction of the current is indicated by an arrow. It's worth pointing out that an electrical current can only flow between 2 points in space where we can measure non-zero voltage points. The reason is that electricity is a flow of charges which requires work, and the measure of workability is the electric voltage. In short, without voltage, there is no current. But beware, the reverse is not true. Of course, a non-zero voltage between 2 points does not guarantee a charge flow. Continuous electrical current can be generated by a circuit whose main parts are the battery, the conductor, and the consumer. At the negative terminal of the battery, there is an electron excess. At the positive terminal, there is a lack of electrons because of the chemical processes taking place there. When connected to the consumer with wires, the electrons from the negative terminal flow through the conductor and the consumer, reaching the positive terminal of the battery, trying to equalize the charge difference. The battery replaces the electrons at the negative terminal with the chemical processes taking place in it. The atoms of the conductive materials are in a stable metal grade. The flowing electrons collide with them during their movement, so they pass on some of their kinetic energy to the bound atoms, which causes a rise in the temperature. The electrical energy of the battery is converted into the kinetic energy of the electrons, some of which are converted into the thermal energy during the collision, leading to a rise in temperature. Conductors of different materials and geometries inhibit electrons in their motion to varying degrees. We use the concept of resistance to describe this property. Its symbol is capital R, its unit of measurement is ohm, which is represented by the Greek capital omega. The displayed so-called Ohm's law states that the resistance value can be determined as the ratio of the voltage on the conductor and the current flowing through it. It also follows that if current flows through a conductor and the resistance between 2 points is not zero, then a voltage drop can be measured between these 2 points. In electrical circuits, there is often a need for a component that has a deliberately higher resistance than the wires. These components are called resistors. There is a separate word for the component resistor and the physical quantity resistance. Resistor is a component often used in electrical circuits, often because of the limiting role of a constant current. Let's talk about the definition of electric power. We've already found that if current flows through a conductor, then heat develops, which is called Joule heat. If we measure this current and the voltage between the 2 points of the material, then from them, their product we get is the heat output. As the formula shows, P equals U times I. However, it's worth to express the current and the voltage in the Ohm's law and replacing them into the formula of power. P equals I squared times R, and it equals U squared over R. This shows that electrical power is directly proportional to the square of the current and the square of the voltage. One more thing to mention in this connection: the wires also have resistance, and therefore heat develops. For example, when choosing the size of wires connecting household appliances to the network, it should be taken into account how much this heat generation will heat them up, as there may be such a high temperature that the insulator surrounding the wire will melt and cause a fire.
Amely esetén a vezetéket körülvevő szigetelő megolvad és tüzet okoz.
I will now talk a little about the electrical sources that provide the energy needed for the charging current. In electronics, we distinguish voltage source and current source. A voltage source is a device whose voltage is constant between its electrical terminals, even if current flows through it. In contrast, the current source changes the voltage between its terminals so that the characteristic current flows through it. I find it important to add that the terminals of the voltage source must not be short-circuited, connected with a low resistance wire, because then a very high current will flow due to its almost constant voltage, and this can lead to breaking the device and also to personal injury. In everyday language, the galvanic cells and batteries are commonly referred to as current sources, although they're much rather voltage sources, especially from an electrical point of view, as during load, a near constant voltage can be measured on them. From an electronic point of view, we cannot produce a current source in real life with simple electrochemical methods, such as galvanic cells, but surely we can with the help of a suitable electrical circuit.
So far, we have talked about direct current and direct voltage. Ideally, this means that the voltage and current in each case are unchanged at all times. I think in reality, such a situation does not exist for a long time.
You're right. In fact, there are cases where we only need a well-defined way of varying voltage and current. For example, machines that operate on the basis of electromagnetic phenomena, transformers and motors, require sinusoidal alternating voltage and current. Without them, it's difficult to imagine, for example, the production and supply of cheap and powerful electricity. The alternating voltage is a special case where the voltage measured at the voltage source is positive, then a while negative, and then it is periodically repeated. The figure below shows the representation of a sinusoidal alternating voltage in a Cartesian coordinate system. The time on the horizontal axis and the value of the voltage on the vertical axis can be read. Since the value of the voltage depends on time, such functions are called time functions. Periodic time functions have a period of time that shows how long a repetitive part of a function lasts. Typically, the period of time is denoted by the letter capital T. In the example above, the period of time is 0.5 seconds. The rate of repetition of the function is usually characterized by the so-called frequency, which shows how many times the periodic function part is repeated in 1 second. Frequency is indicated by the letter small f. The unit of measurement is hertz. It is represented by Hz. Frequency is reciprocal of period of time, i.e. the frequency of the function in the above example is 2 Hz. F equals 1 over capital T written down. We can see that 1 divided by 0.5 actually gives us 2 Hz. The voltage time function shown in the above example can also be described as an equation with the help of frequency or period of time. In our case, capital U of t can be written down as U of t equals 3 times sinus 4 pi times t.
This brings us to the end of the third video in this chapter. We welcome you all back in the fourth and final video, where you will hear about the tools we use to describe the voltage, current, and resistance characteristics of a circuit mathematically. Goodbye!
Sziasztok!